And again, if you're going to get lost in the notation, which you probably will, but we're going to go over the important ideas, and you can go back and fill in the blanks at home. Here is a surface. Could that potentially model the temperature of a certain place? Like on the origin, the temperature is pretty hot, and then as you go, maybe this is the maximum. I don't know. This isn't necessarily. How do you know? Actually, this can't be the maximum. Why not? Why can't the maximum
keeps going up?
It's still going up in a direction, right? You see that? Like the derivative here is not.
It has to be 0.
Yeah, to find a max, you'd have to have a tangent plane parallel to the xy plane. So the point is, what we're looking at here is we have this point x naught, y naught, z naught, so our initial point, and we're taking the directional derivative in this direction. So far, we've only gone in 2 directions, parallel to the x-axis and parallel to the y-axis. Now we need to learn how to take it going in any direction. What type of vector is going to come into play all the time? Unit vectors, and we really like them, and here's another reason why we like them. Okay, so what's fx? What is that one? 2x y to the third. Nice. What's fy? 3x squared y squared. And keeping it in alphabetical order is really, really helpful for me. It's one thing I really should have specifically told you to do on that that quiz, on the one where you had to take all the L, M, X, and Y. Oh, I forgot about how much fun that is. Okay, so now that we have the partials, what should we do now? Plug in what? Which point? 2, -1. Yeah, okay. So we get fx at 2, -1 is what? -4? I think it's -4, right? Yeah. Fy 2, -1. What's that going to be? 8? Good job. Okay, so we have those, but what else do we need? We need what? Unit vector. Unit vector. We love unit vectors. Love them. Love them, right? We have our directional vector v. Is that a unit vector?
No.
No, it is not. What is the unit vector u going to be? And someone just tell me this off the top of their head.
V over v.
Ah, thank you. 29. Root from? You see that, right? So there's u. So what are you dotting together here? You're going to dot -4, 8, and you're dotting it with 2, 5. But what's that thing on the outside? Does it matter if I put the root 29 on the outside or on the inside? It doesn't matter, right? So if you dot these things, what are you going to end up with? -8 over root 29. Ah, how did I get root 29? The magnitude of v is root 29. So to make it a unit vector, we have to divide by the magnitude. U is equal to v over the magnitude of v. Again, I don't know why they always use u and v, considering they sound alike and they look alike, but sorry. So what do I end up here? End up with -8 over root 29 plus what? 40 over root 29, so that equals over 29. So that right there is the directional derivative of that function in that direction. Key being, please, please, please use a unit vector. That's it. So just to say that one more time on the record here, we're adding a dimension in. We're not changing anything about the process. Go ahead, Jeff. Direction of the gradient. Exactly. That's from chapter 12. The point being, if you want to maximize the rate of change at a given point on a surface, the maximum is going to be the gradient. Does that make sense-ish right here? Are we okay with that? We decently okay? Okay, it's fine. Now that we have finished this, it tells us that it gives you the amount and it gives you the direction, because if you want the direction of the greatest, fastest rate of change, which direction do you go in?
Gradient.
The direction of the gradient. That's correct. How are we doing? Okay, we awake here? We're doing okay? We're feeling okay with this? Okay, let's do a practice. Find the partials, yeah. So fx, x, y, z. What's that going to be, Jerry?
That will be 1 over 4, 2x. So 1 over 2x.
So x over 2,
Yeah.
right?
And
Fy of x, y, z, 2y, and fz of x, y, z, 2z over 9.
What are you taking that with respect to? I mean, not with respect to, but you know how it's only like f sub x? There's no like function. It's just all So what are you taking the derivative with? Not respect to, you know what I'm saying? Yeah.
What kind of differentiation am I doing?
D what? Oh,
The partial.
now you need a function, you do partial derivative.
Yeah, exactly. So when we did this kind of thing, what did we call it in Calc 2?
Implicit.
So you can call this implicit partial differentiation. Is that better for you?
Yes.
Okay. So if we wanted to write this equation, what's the next thing we need to do? Yeah, you're taking this and just plugging it into each of these. So we're plugging in -2, 1, -3, and what do we end up with? We end up with -1 and
Yeah, -2/3.
thank you. Okay, so what's the equation going to be? -1 times what?
X plus 2.
Thank you.
Plus 2. X plus 2.
X plus 2? Oh, it's -2. Thank you. I was looking at the wrong column. Thank you. I'll record this part here. Oh, it is recording. Good. So we have x what? Plus 2. 2 times... Is it y minus 1? Yep.
It's right there.
Oh, it's right there in front of me, isn't it? Negative. Oh, z. I love it when people say z.
What's that?
Z. It's z, but like in the rest of the world, everybody says z.
Canadian, right? Canadian.
Z minus what? Plus 3. Equals 0. There it is, right there. We like it in this method of writing the equation of a plane. It's equal to 0. That's correct. Could you multiply this out, clean it up a little bit, put the constants all together? Sure, you can. But can you also leave it like this?
Yes.
Absolutely. This is the tangent